Hey, hi everyone. So, in continuation to our study towards an AI, we have covered the flow machine learning, introduction to machine learning, intelligence, linear regression, logical regression, decision trees, random forest, SVMs, and we also covered. Maybe I should grab my headphones and also close the door. That's better. So we have covered SVMs, decision trees, random forest, and then SVMs. What else did we cover? Naive based, probability based distribution, and that's it, I guess. Yeah, that's what it said. And then we looked at variance bias, underfitting, overfitting, and then we looked at metrics on how to measure these. Oh, sorry, we've also looked at unsupervised k-means clustering algorithm, and we looked at yeah, metrics to measure this model accuracy. uh, we looked at classification problems, and for them there is accuracy, there is confusion matrix, expression recall, F1 score, specificities, which is nothing but it's a 1 minus recall of negative. And then we looked at ROC graph, and AUC, area under curve. Um, mm, so that's the thing metrics that we have classified for looked at, um, classification. So today we'll cover the metrics for regression problems. And how do we cover it? Most probably we have looked at it already. It's quick recap. That is, there is something called MAE, which is mean absolute error, which we have seen during linear regression times, where the absolute values are being, we take a mean of the absolute differences in between y and y predictor and stuff. We also have looked at MSE, mean square error, that is absolute uh, difference squares, mean of absolute difference squares. Okay, so let's look at them and then study. Okay, let me share the screen. Okay, let's look at there's a blog post, man. Did I say it or not? Maybe I would have closed it. It is actually a good one. It's explained all this metrics. Okay, now let's look at mean absolute error. That's when discussed. This is the formula. minus yi, mod of yi minus yi. Uh, Mean square is sum of y minus yi whole square by n. Root mean square is square root of MSE. It provides a measure of the average magnitude of errors in the same units as the target variable. I often preferred because it is more interoperable than MSE as it is the same units as the target variables. Okay. Mean absolute percentage error. MAPE measures the average percentage difference between the predicted values and the true values. It's a measure of the relative accuracy of the prediction and is fairly useful with the different scales. Coefficient of determination R squared. R squared. This is important. Coefficients of determination R squared. R squared measures the proportion of variance in the dependent variable that is explained. Mm. Mhm. The sum of squared errors and the sum of total sum of squares. Squared errors by total sum of R squared value ranges from 0 to 1. Indicates a perfect fit and 0 indicates these metrics are different perspectives on accuracy and means of the physical. R square is coefficient of determination. Yes, that is very useful. It actually explain. Use Google also at the same time. Okay, so statistical measures determine the difference of regression model indicates the proportion of the variance in the dependent variables. It means how well the independent variables explained the variability of dependent variables. This was carried as the ratio of explained variance. Of squared errors to total sum of squares. Errors range from 0 to 1. Dependent variables, independent variables. You should understand what it is. Image of it meaning that it does not provide information about the absolute, but rather compares the fit to the model to a baseline model. Model. Overall aspect. Okay, let's see now. Top evaluation metrics.
I cannot find the bracelet.
Problem is a common type of supervised learning. Residual. Okay, directly jumped into top evaluation metrics for the question on
Found it.
R-squared or R-squared is a statistical measure that tells us how well a model is on scale.
Not that one. Not this one. First, first.
RSS by TSS. That is the sum of squares of residuals. Residuals by is the actual value and by value, and TSS is minus y dash square, where y is the actual value and y dash is the mean value of that is like x1 plus x2 plus x3 plus xn by n. Hmm. How is that being used? Doesn't even make sense. What does it mean? How is that being used as a metric? How to score to get accuracy of your model on a scale, just like in classification model. Implement tab to score. No, there is something wrong. So actual values, predicted values. Here he says this is our actual values. These are predicted values. This is fine. Is the mean value of the variable slash feature. Other features. Where is the mean value of the features here? They don't even have mean value of features. We should get to the math of it. RMSE R square, adjusted R square. Ganesha is there. R square can be calculated using the equation below in which is the mean. Mm. The mean value will be considered the baseline value. Let the baseline error as the square error differences between the actual y and the mean value. Oh, does it mean it is like mean value is y plus yi by 2 2 with the 2yi yeah, it's just like r square is going to be just r square in this equation of data samples, infinite variables, number of data samples minus 1 by minus k minus 1 by. Oh, you show me here. R square adjusted R square mean square of RMSE. Mean absolute error, residual standard error, mean absolute deviation, maximum residual error, root relative square error, based in information criteria. Palos CP assesses the fit of regression model against expression correlation coefficient measures how strong they are. Classification accuracy precision recall reference score confusion matrix ROC AUC. Yeah, covered everything. So this is good. This is good. Coefficient of determination R square. Start of the finding residuals. Land at each point or for the predicted y value by plugging in the corresponding x value equation. Okay. Actual value is residual is negative, residual is positive. Okay. residual square we need to sigma to find the YML. You first need to find the mean of Y values. Two, 4, 6, 7. Mean of Y value C means mean of actual values. Means we are looking at each value's distance from the mean. How far are they distributed from the mean values? Minus. 1 minus sum of square residuals by sum of squares. Mean of actuals, and that's what he's supposed to write. This is nice, very clear. Sum of square root error residuals differences by sum of squared actuals minus mean of actuals. That's called R square. Last time also we have seen this. I forgot. We forgot to next time. We forgot that something called as R square is there itself. It is not nice. R square and adjusted R square. Adjusted R square is 1 minus 1 by. Okay, I think we've covered everything. Adjusted R square. We can see if you want to. You only need R square. None is the number of points in your data sample. It's the number of dependent. Registers will penalize you for adding independent variables. And add more variables to the data as you think of them. Some of the variables will be significant, but you can't be sure that significance is just by chance they existed as square root. That's extra. While values are usually positive, they can. Now here it is clear now. So if you look at this, the individual values is okay. So I'm not going to calculation now. Lesson data. Number of predictors P, sample size. Means if there is an equation, for example, an example of adjusted R square, let's look at example intercept. Yeah. On 10 data sets. Um, adjusted R square maybe. Yeah, just to be clear, that's why to leave this thing. Okay, let me share the screen and do it better. Version of the coefficient of distribution R square. Never mind. Model of 0.5 and 0.75. Under observation, we want to fit a multiple integration model and house prices based on various features such as size, sun location, let's say. Number of features, that's all. So saying number of all features, that's all. X1, X2, X3, number of features. The number of independent variables predictors in the model. Dust of R square calculation K represents the number of subpredictors in the regression model. For to has features are inputs in machine learning terminology. Okay. Number of independent variables K corresponds to the number of coefficients that model fitting each independent variable contributes a coefficient to the model. So he says number of variables and number of coefficients are all the same. Okay. K represents the number of features or variables that are included in the equation, regardless of whether there are parameters. These variables could be numerical features, categorical variables, and included as dummy variables are when calculating adjusted. On the this is the addition of necessary predictions. Degree of randomization of estimating the value. That's a more accurate model. Fit. Got it. I think now we're good. We could cover. We thought we could cover PCA also. PCA is an important topic, so let's try to brief PCA and see. But to repeat on what we have done with respect to evaluation of regression models is we looked at residual is nothing but y minus y or error with respect to what is predicted to what is the actual value y minus yi. Um, um, MA is mean absolute error, that is absolutes of the y minus I, so that the negative differences doesn't impact the positive differences and vice versa. And mm, mean square errors, MSE, is where you have mean of squares of differences, residuals. Um, that actually helps in amplifying the ones where there is more differences. Root mean square error is done. RMSE is to take a square root in a way that it actually equates the values closer to the actual y values. So mm, the differences are closer to actual y values. And we are amplifying the difference, but at the same time we are reducing the value when we are saying the value. That is root mean square error, and then R square and registered R square. R square is where we have 1 minus sum of squares by actuals minus mean of actuals square. Sum of actuals minus mean of actual square. Um, why are we doing mm, coefficient of determination is what R square is called. But the question is, why are we doing this y minus a minus mean difference between the actual value and the mean of the actual values will give us more like distribution, right? How much it is distributed from the mean, how much these values are distributed to that of the errors. Hmm. Now it's becoming dependent on the number of data sets and stuff, right? Like if you do uh, distribution, let's say you add one more value, the mean will become more, and your base will become more, and then if your base becomes more, this becomes lower, and your accuracy will increase. So just by adding more data to the data sets, we can actually increase the R square error. Um, you adding more features will also increase your actual prediction. Sorry, you adding more features will also increase the y value. Not necessarily, right? More features doesn't mean with split be negative, it can reduce also. Mm, I don't know how number of features will influence the number of features. That's the only way, right? Number of features. See, y actual minus mean of y actual, all of them are um, standard values. They are not variables. They are non-variables, right? The variable one is the y predicted, because y predicted in turn depends on features. Features can change and the weights can change. So y predicted can change. Y predicted is the only one which will change. When we change the number of features or the corresponding weights, the y predicted will change. The rest of the equation will always same. So n minus 1 by n minus k minus 1. So number of features is okay, but number of features minus number of data set value minus kn minus 1. This is making me curious. We should listen to an explanation from somebody on R square and adjusted R square. Okay, I'll try to find out more information, and I'll let you know, guys, if I have anything interesting to share tomorrow. Uh, but meantime, if you look at PCA, principal component analysis, it's very called principal component analysis system. And okay, principal component analysis dimensionality reduction technique, widely used in machine learning and data analysis to transform high dimensional data sets into a lower dimensional space while preserving the most important information in the data. PCA achieves this by identifying the directional principal components along which the data varies the most, and projecting the original data onto these components is a detailed explanation of PCA. Motivation in many real world data sets, especially those with a large number of features, there may be redundancy or collinearity I don't know if second L is important there, but among the features, making it difficult to visualize or analyze the data effectively. PCA aims to address this issue by reducing the dimension of the data while retaining as much of original information as possible. Okay. As I mentioned, but like there are too many features, we are trying to reduce the features. That's all. Simply. Principal components. Principal components are the orthogonal vectors that captures the direction of maximum variance in the data. The first principal component captures the most variance, followed by second principal component, so on. PCA 6 the maximum variance of the data along with external maximum variance. PCA what patterns in the data. That's orthogonal to when you say orthogonality in between the okay. PC typically starts with standardizing the features to have zero mean and unit variance. This ensures that each feature contributes equally to the analysis and presence with larger scales from dominating the principal components. Okay, so across all features independently, x1, x2, x3, x4, it standardizes it. So mean of you divide standardization of the features to have zero mean. Okay, if some of the values should be zero, that means we should distribute them in between -1 to 1 comma 0, -1 to 1 in a way that needs to be 0. That means we multiply each value with how do we do standardization now? One. This is very bad. We'll look at it. Okay. Covariance matrix. PCA. It's the covariance matrix of this, and it's the pairwise count. Okay. I think I should stop. This is important. PC is very important with respect to how the models are formed. So I would like to spend more time here. So, oh, I'm not sharing the screen. Great. So I'll stand the stream here. We'll catch up tomorrow.